Hello and welcome to another video in this series as together we learn the basics of Lean in order to write simple maths proofs. Today we're going to be looking at recursively defined functions, how to define them and how to work with them, and we'll also see the connection between recursion and induction. We won't go into a lot of depth, but we'll just see that there's a connection and it might be something we explore later. So let's dive in. So what is a recursively defined function? It's one of those things where you know it when you see it, and the technical definition can be a little bit dry. So let's first look at an example, and I think that's the best way to kind of understand what we're talking about. So the Fibonacci sequence is quite famous. It's linked to lots of shapes in nature, proportions, the golden ratio in architecture, in design, as well as appearing in natural forms like plants and so on. The sequence is this one, and it goes on forever. Each number is worked out by adding the two previous ones. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. You do have to start by defining the beginning in some way, so 1 and 1 are just defined. Then after that we follow that rule. So that's an example of a recursively defined function. There are many others. Some of them are actually simpler. This isn't the simplest one because this is using two previous values. Simpler ones will just use the previous value, and that's what we'll look at today. So let's look at a task that we're setting ourselves, and that'll frame our discussion today. So this fn is a recursively defined function that maps, well, it takes a natural number and outputs a natural number. It maps from naturals to naturals. And this thing may be unfamiliar if you've not seen it before. It's a way of assigning values, deciding what the output is, by giving some rules. And it's saying that if the input is 0, n is 0, then the output is 0. Otherwise, for any other case, then the output is 2n minus 1 plus, and what's this? fn minus 1. That's the previous value of fn. We'll bring this to life in a second, but at this stage the main point to kind of see is that this is defined by a set of rules, and there's just two rules here. You can have more, and the rules are dependent on what n is. So if n is 0, that's the output, 0. Otherwise it's this, and we could have if n is 1, if n is 2, but this is a simple example, so we've only got two cases. And our task is to prove that this recursively defined function has actually a simpler, neater, what some people call a closed form, which is fn is n squared. Now that sounds almost too good to be true. Surely something like this, which seems kind of discrete and a bit unruly. I mean, this is not the most nice looking expressions. How would this, the output of this, the sequence generated by this, could it be as simple as n squared? Well, we have to prove it, and the suggestion is that it's true. So that's exciting if we can do that. But before we do that, let's just practice working with this kind of definition. So if you want to, I'll use pen and paper now, but if you want to read this in slower time, the slides are online, or you can press pause on the video. But let's do this ourselves. So we said fn equals, it's 0 if n equals 0, and it's 2n, was it minus 1? Yeah, 2n minus 1 plus f n minus 1, and that's the previous one, this one, fn minus 1, and that's fn. So that's otherwise. So let's start with well, we have to start at 0. We can't start at, say, f5 because we'd need f4. So let's start with 0. If n equals 0, then f0 is 0 because of this rule. If n equals 1, then f1 equals, it's this rule now. This is always going to be the rule that applies. So it's 2 times 1, because n is 1, minus 1 plus f. n minus 1 is 0. So that is 2 minus 1 is 1 plus 0, which is 1. Let's do n equals 2. So f2 equals 2 times 2 minus 1 plus f1 equals, that's 4 minus 1 is 3, 3 plus 1. Remember, this one comes from, that one goes there, that one goes there, and so on. So this one will be 4 minus 1 is 3, plus 1 is 4. N equals 3. This does look like n squared, doesn't it? f3 equals 2 times 3 minus 1 plus f2. So 2 times 3 is 6, minus 1 is 5, 5 plus 4 is 9. So far seems to support that theory, doesn't it? But examples aren't proof. We need to prove it. But this is just to show you how this kind of definition works, how we can evaluate that function for values of n. Right, so, oh, by the way, just to go back to that definition of recursion, we won't do a very technical definition, but it's recursive because it's each value is derived from, is calculated from a previous value. So fn depends on f at a previous value of n, except maybe the first case or the first few cases. So in this one, f0 was defined non-recursively. In the Fibonacci sequence, the first two were defined non-recursively, but generally the rest of them then are defined informally in terms of itself. And it's worth also just pausing and thinking about, well, this looks like induction, doesn't it? Or the process of induction, because you remember we had a base case, the proposition for n is 0, and then we had Pn implies Pn plus 1. The proposition for n implies a proposition for n plus 1 as a way of going from 1 to the next value of n. This looks similar. We've got a base case, so f0 is defined, just as we have a base case that's easier to show or prove in induction. And then we have something that allows us to get from fn to fn from a previous one, fn minus 1. So there seems to be a similarity here in terms of the process or the mechanism. So let's hold that in our heads and we'll come back to that. So it's not immediately obvious how we prove this, but we'll try induction. And as we know from last time, you can prove surprisingly interesting things with induction that would otherwise be quite a messy algebraic challenge. So if we're going to do this by induction, we have a proposition which we'll say Pn, the proposition for n, is that Fn equals n squared. In fact, that's what we want to prove. By the way, if you're not familiar with induction, the previous video was all about induction, introducing it, so go back and look at that one, and the blog is more carefully written if you want to take your time and read that yourselves. So yeah, do go back to that if you're not familiar with it. So this video assumes you've been through that. So as we know with induction, we need to prove the base case and an inductive step. So the base case here for n is 0 is the proposition that f0 is 0 squared. Actually, let me do this with pen and paper because this screen is a bit overwhelming. So we want to prove that Fn equals n squared. So let's say the proposition for n is this. That's what we want to prove. And to prove this by induction, we prove the base case, and we need to prove the inductive step, which is that Pn implies Pn plus 1. So let's look at these in turn. So P naught is the proposition for naught, which is that F naught equals naught squared. Is that true or false? Well, we know that F naught is defined by definition as 0, so 0 equals naught squared, which is true. Why is it naught? Let's go back to our definition there. So if n is naught, then F naught is naught, so it's by definition. And this one, to prove A implies B, we assume A and derive B. That's how you prove an implication. So we assume Pn, so we assume Fn is n squared. That's what we assume. And we now need to derive the Pn plus 1. So Pn plus 1, let's look at it. What does it say? It says that Fn plus 1 equals n plus 1 squared. So let's start with what the definition tells us. It tells us that Fn plus 1 is 2 n plus 1 minus 1 plus Fn. That's from the definition. Where's that? There. So if we plug n plus 1 in, Fn plus 1 is 2 n plus 1 minus 1 plus Fn, because Fn minus 1 applied to n plus 1 is Fn. So that equals 2n plus 2 minus 1 plus Fn equals 2n minus 1 plus an Fn, which we're assuming the induction hypothesis, we're assuming Pn is n squared. So that is, so if I say n plus 1, because we know that's what we're trying to get to, that's n plus 1 squared. What is that? That's n squared plus 2n. Ah, that's my error. That was a plus 1, yeah, so that does simplify. I made the error there in algebra. So that is actually Pn plus 1. So we've shown that is true. We've shown that Pn plus 1 is true, that Fn plus 1 is indeed n plus 1 all squared. So by induction, we've proven it. So what's new here isn't the fact that we've done an induction proof, because we did that last time. What we've done here is use a recursively defined function. And where did we do that? Well, we did that here because we went to the definition of Fn, and we did that here where we use the definition of Fn. In fact, here was F naught. So that's new. We're using a recursively defined function. We just happen to be doing an induction proof about it. And again, what's interesting to me is that what we're proving appears to be kind of continuous, n squared, a quadratic kind of expression, whereas the recursive definition seems to be very discrete, a sequence generator. So I think for me that's kind of interesting. So it's always useful to write this out in small steps, because it helps prepare for lean proof. We've been doing that with all the videos in this course, and although it can feel a little bit laborious, it helps plan out and take us halfway towards the lean proof. We need to think about what the proof objective is, what the kind of hypotheses are that we're assuming, and so on. So this is a standard induction proof, so nothing new. It's what we did in the last video. What's new is that we're using the definition of a recursive function. So the code is a little bit longer. I had to split it onto 2 slides here, and rather than sort of talk about it here, I'm going to live code, and then I'll come and check that I've made every point that I wanted to. But very briefly, what I've done is I've created the definition of fn, which is the recursively defined function. I'm going to evaluate it at several points just to check it does what we expect. And then we've got the actual proof of our theorem that fn is actually n squared. So all of this code is online as well on GitHub. You can download it. In fact, if you download it, it brings with it the config files for creating your kind of lean environment, so you can get up and running easily. So this is the definition of a recursively defined function, and it looks new. This structure is new to us. We've not seen this before, although it looks a little bit like an induction proof that we've seen before. So there's some similarities there. We define it and give it a name. We say what it maps from and to, and then each of the following lines then is the cases, and then maybe more than two, as we said. So it's easy to see here how this works. 0 maps to 0, and n plus 1 maps to this expression here. Now, why is that different? Let's go back to pen and paper. So in our maths definition, we had fn equals 0 if n equals 0, or we had 2n minus 1 plus fn minus 1 otherwise. But when we're writing lean code, lean definitions, we can't use fn minus 1. It's not a problem really in the maths, because fn is a natural number, n is zeros defined here, and then for n 1 and greater it's defined here. So you never get the case where you get 0 minus 1. But that isn't how the lean definitions work. It could be something that improves in future, but for now we can't say fn minus 1. So that's not a problem, that's okay. We can actually just increment n. So here we've got n mapping to 2n minus 1 plus fn minus 1. If we increment n, that will then give us n plus 1 maps to 2n plus 1. We're increasing every instance of n, minus 1 plus f. n minus 1 plus 1 is fn. So that's legal in lean anyway, because then that goes 0, 1, 2, 3. Whereas here, 0 minus 1 would have been problematic. Okay, so does that behave as we expect? Well, eval, this hash eval, is a way of evaluating an expression. So if I said 2 plus 3, or 2 plus 6, that's 6 there, it shows the answer in the info view. 2 plus 1 is 3, 2 plus 11 is 13. So it evaluates this expression. So f applied to n, that's how you write fn. Well, we don't know what fn is, so f applied to 0, we know that's 0. f1 is 1, f2 is 4, we calculated that before. f3 is 9. Let's see, f10 should be 100 if that theory is correct. Yep, f10 is 100. So this is just checking that our function is behaving as we expect. It's not a proof that's correct, but if it's definitely not giving you what you expect, there's something wrong. It's a good way of checking your work as you go along. So that's what eval does. There is, just as an aside, another common hash special instruction called check. So if I say it checks the type of something, so check 3, it says it's an integer. Check f, it's a function from n to n. So that's a useful thing to have, checking the type of things. If I say check f2, what do we think it's going to produce? So f2 is 4, which is an integer. Let's try it. Yeah, f2 is an integer. Is a natural number, sorry. Yep. So that's useful. So eval f3. Great. So now we've got our theorem, which is that fn, f applied to n, is n squared for any and all n in a natural number. And you can see there's similarities here between the definition of a recursive function and the structure of an induction proof. There seems to be something that looks like a base case and then the kind of inductive step. So again, worth kind of just putting that in the back of our minds. So let's fill it in. So for the base case, we have to prove f0 is 0 squared. So how do we do that? Well, we'll do it with a calc section. So calc, and we're interested in showing what f0 is. And f0 by definition is 0. How do we refer to that definition? We use RWF. And that's the, is that justify thing? By. So that's saying f0 is 0 justified by the definition of f. So RWF will go and look inside f and find the appropriate row, the proper case, and pull back and use the right hand side or the left hand side if there is one. And then we can say that is indeed 0 squared, and that's by norm num, which is just simple arithmetic. So that's great, we know that. And for the induction step, again a calc, slightly more involved, bit of algebra, but we've done it in the maths part already. So we want to prove, in fact the goal state tells us, if we forget, it tells us that we can assume fn is n squared. That was the inductive hypothesis. And we need to prove that f of n plus 1 is n plus 1 squared, just in case we lose sight of what we're trying to do. So f n plus 1 equals, and we're going to use the definition which tells us that it was 2 times n plus 1 plus fn, and that's justified by referring to the definition f. Nice. And then we can use the inductive hypothesis. So that's 2 times n plus 1, and fn we know is n squared by the induction hypothesis. So plus n squared by rewriting using the, or substitution using the induction hypothesis. Great. And by algebra that's n plus 1 squared. So by ring. Job done. Nice and easy. Brilliant. That's it. Easy peasy. So that wasn't that hard actually. So again, we were doing an induction proof, which we've already done, but we were applying it to what looks a little bit like a more challenging definition of a function, but it turns out to be relatively easy. So just worth pointing out, we're not going to dive deeply into this, but we saw earlier that the recursively defined function, the way we evaluated it, looked a bit like the induction process. We had a base case, f0, and then for other cases we evaluated it n by using the value at n minus 1, and that gives us, you know, a chain reaction that can give us all the values at any larger n. And then there's also that similarity between an induction proof as we write it in code and a recursively defined function. They both seem to, well, let's look at it again. They both seem to have these bars and a base case and a kind of a next step case, a base case and a next step case. So that's worth kind of pondering on. The two actually are related, clearly, and we won't go into today, but inside Lean, induction and recursion are unified. They're implemented in the same way. That might be a topic we come back to later. It's a little bit more advanced, defining types that are inductive and seeing how that's related to recursion. So that might be something we might come back to if there's demand for it. But for now, we just wanted to recognize that there's a strong similarity there and it's not accidental. So the easy exercise, we say easy not to be kind of patronizing, but the idea is not to have a maths problem that is kind of torturous from a maths perspective. It's supposed to be an easy maths problem, so we get a chance to practice using lean. So let's see how we might do this. I'm not going to do it for you, but I'll talk through it. So let's try and talk through the maths of this. I won't do the lean code because that's your exercise. So we've got a function gn which maps from the natural numbers to, that's a single arrow, not an implication, to the integers. It shouldn't be problematic that we've got integers there. And its value is defined as two cases. 0, no, it's not 0, it's actually, what did we say it was? It's 1. It's 1 if n equals 0. And otherwise, it's -1 times gn minus 1. So it's the previous value multiplied by -1. Okay, and our proof objective is that gn equals -1 to the n. That's what we're trying to prove. So it won't surprise you that we're going to try induction. So if you've got a proposition n which says that gn equals -1 to the n, that's what we're trying to prove. And we do that by induction, which means we have two things to prove: a base case that p0 is true, and then we'll do an induction step that pn implies pn plus 1. We'll do that next. So first we'll focus on the base case. So p0 is the statement that, the proposition that g0 equals -1 to the 0. Now what is g0? g0 equals 1 by definition, equals -1 to the 0, because that's 1 as well. So the base case is true. 1 equals 1. Now, to prove an implication, as you know, to prove A implies B, we assume A and then derive B. So what are we assuming here? We're assuming the inductive hypothesis that Pn is true. That is, Gn equals -1 to the n. And we want to prove something about, we want to prove that Pn is true, Pn plus 1 is true, which is Pn plus 1, and that says that Gn plus 1 equals, well, let's write out what the definition is. The definition of Gn tells us that's -1 times G n minus 1 plus 1, so that's Gn, equals -1 times, and Gn is the inductive hypothesis, tells us is -1 to the n, -1, oops, to the n. So that comes there, and that's simply -1 n plus 1. So that is actually Pn plus 1, so Gn plus 1 equals -1 to the n plus 1, and that is the proposition Pn plus 1, so that's proven. So you'll do this in code, and this algebraic step is actually really easy. It might look like this is a contrived, difficult example, but I've actually contrived it so that the algebra is really easy. I would say it's even easier than the example we looked at. So you can see it there, and your task is to turn that into a lean proof. So have a go at that. I hope you found that interesting. So just to recap, what was new today was not induction proofs, that was last time, but the idea of a recursively defined function, how we write them in lean, that thing to avoid about not having n-1 in the definition, and then how to refer to the definition in your proofs using RW. So that was new. See you next time. Bye.